I'm Dr. Ben Britton. I am the Characterization at UBC Cluster Lead and a Professor in Materials Engineering. Today's seminar we are broadcasting from and at the Vancouver campus, which is situated on the unceded territory of the Musqueam people. We recognize that people online may be joining from other traditional territories. This is a continuation of our regular seminar series over the summer. We have a few more scheduled, exciting coming up. But today it's a great pleasure to introduce Mike Fussell from Zaber Technologies. A little bit of background, I'm sure he'll give a proper introduction of the company, but we've been, at least from my side of the world in UBC, growing collaborations with Zaber Technology through a variety of things, in particular with work led by Professor Adam Clare and colleagues. But Zaber have a long history with UBC. They are based in Marple, not too far from here in Vancouver, and were founded in the late 1990s, I think, by a group of individuals interested in bringing together automation and controls, and this overlaps with characterization, as Mike will talk us through, with effectively a new way of thinking of optical microscopy in those technologies. Mike is the Life Science Product Manager at Zaber Technologies and has a specialism in lab automation with the Nucleus automated microscopy platform in particular, which is optical with fluorescence and other technologies. Again, we'll see that in a bit. I'm going to stop talking now and leave it to Mike to take us away. Thank you.
Fantastic. Well, thank you very much for having me, and thank you for joining on a perfect sunny summer afternoon with the World Cup game. So yeah, thumbs up there. So I'm going to be talking about how automated microscopy can help you with high throughput characterization workflows. And we'll be sort of looking at Zaber's Nucleus platform. And so quick background. Background in biology from the University of Alberta, and then a master's in biotechnology commercialization from the University of Auckland. And after that sort of biotech-focused start, I spent the next 5 years working for Point Grey Research and then FLIR in their industrial machine vision group. And so then with Zaber, bringing biotech, life science, commercialization, imaging technology all into the microscopy platform. So that's sort of where I'm coming from. What I wanted to do with this talk is just give a brief introduction to Zaber, local company that's got a long relationship with UBC. Then kind of talk about a brief introduction to Zaber's automated microscopy platform. And then I want to give you an examples, just some of the cool stuff we can do and the things we can do to enable interesting sensing modalities to really support your research with things that you cannot buy off the shelf, and just get your imaginations going and show you, yeah, we love a good weird microscope. And so, yeah, like we'll give you some examples, but that's really just a starting point. And then I want to take a few minutes to look at sort of some of the foundations of really that high throughput side of automated microscopy, and thinking about where it makes sense to optimize and how where it makes sense to optimize. And I am leaving an instrument here for a few weeks. So we'll do a really kind of crash course in how to actually use that instrument, so that if you want to try something out and have a go, you've already got kind of what you need to get started there. So Zaber, yeah, local tech company. We are, sometimes feel like we're kind of one of Vancouver's best kept tech secrets. The company's grown really quickly. We're just at the bottom of right at the bottom of Cambie Street in Kent by the Marine Gateway SkyTrain station. We've been making microscope stages for 11 years. and making microscopes, complete microscope systems for about 6 years now is when we made the first prototype. We were founded back in '97 by a couple of UBC engineering grads. And since then, many Zaberians have come from UBC's EE, Mech, Mechatronics, and EngViz programs. So we have a lot of relationships with those faculties and groups. Zaber hosts a lot of engineering co-ops. We do a lot of co-op placements every 6 months. There's a new crowd. So I would also put a plug in if you are looking for any sort of co-op or work experience placement. Zaber is definitely we hire a lot of UBC students, and I think it's a great place to be from. We also have a long tradition of supporting student teams, so Thunderbots, solar super mileage, robotics clubs. So yeah, we do a lot of I think we've been quite involved in the UBC community there. The platform that I wanted to talk about today is, I guess, our Nucleus platform. Rather than thinking of it as a specific product, we really do think of it as a platform. So it is a collection of modules, which they all share common mounting, they all share common control protocols, and we really want to make it easy to mix and match and combine and recombine, so you can build the optical path you need for your work. And then if your research question changes, or you need to add something on, or you finish your project and start a new one, you can take it together and take it apart and put it together in a new way, so it's not in a corner collecting dust somewhere. We have a lot of flexibility in terms of optics, so we can support all the major optical systems, including some of the weird ones like Edmund Optics. That's kind of a bit of an outlier these days, as well as like there's a group out of Triumph that have these like crazy high numerical aperture reflector lenses. And sure, we can fit one of those inside our system. We have two main configurations. So we have an inverted microscope. I think this is more life science focused. So this is really our kind of bread and butter epifluorescence, biology research system. We integrate with confocal scanners. But I think your group is much more on the materials side. And so I think the upright configuration is going to be more interesting for you. We have a lot of flexibility in both the XY, the sample positioning of this, as well as just the layout of the system, because we've separated. We have this sort of big support tower. We can put really big things by just kind of extending all of that. So there's, I guess there's a 200 millimeter wafer there, but we can go up to 300 millimeter wafers. We can put much bigger things. You can mix and match axes. So we've had people doing sort of parts transitioning between multiple stations, where you have a short travel axis, one short travel axis and one long travel axis, so it can move between stations and then move into the microscope and then do your imaging under the microscope. Again, if you're automating workflows besides just imaging, and we'll show you some examples of some of the other parts that we have that can help you with that. The optical paths on the inverted and upright system are the same. They're just flipped around. So by default, we do have the epifluorescence, where we are both illuminating through the objective and getting our light back through the objective. But we can mount ring lights for external illumination. We can do transmitted illumination. We can do dark field. So we do have a lot of flexibility, as well as we can get a couple more interesting sensing modalities as well. The XY stages, just on their own, we've kind of, depending on your need for accuracy, resolution, speed, and size, we've got a range. As a kind of rule of thumb, the stepper motor stages, they are less expensive and quite good. The linear motor stages, the direct drive ones, those are a bit more expensive, but way faster, way more repeatable, way more accurate. So they are overkill for projects sometimes, but if you're doing really high resolution work where you need, like 50 nanometer type step sizes, or you need that really high speed, those direct drive linear motor stages are definitely the way to go. And this should work here. We should have a. So this is one of our higher speed stages. So with line scan applications, we can support like imaging the entire area of a plate extremely quickly. This is sort of, it normally would take minutes to do something like that. And so with line scan cameras, where we can synchronize the line rate of the camera with the encoders on the stage, we get really tight synchronization and high speed scanning. One note about specifications: if you're kind of comparing stages, I guess a quirk about Zaber is we do tend to be extremely conservative with our specs. I've got the specs here for two stages. So one is our we're looking at the total area over the full range of travel, and so in practice, for typical microscopy workflows, you're moving very small steps. So with this ASR stage here, the big spiky one, that periodicity comes from actually the lead screw on it. So that's part of the mechanical drive of that. Whereas the direct drive linear motor stages, they're just flat. There is no conversion of rotary motion from the motor into linear motion. It's just direct linear motion. So you get much higher accuracy, much higher repeatability. But yeah, we measure the accuracy spec we give is like the worst possible case across the full range of travel. People don't really use stages that way. Our competitors also don't measure them that way. So yeah, I would say in practice, the performance you get out of the stages is way better than you might think based on the spec. But yeah, there's the difference between the linear motor and the screw driven stuff. So like highly recommend the linear motor stuff. And that's kind of been a technology that Zaber is getting really good at, and it's kind of one of our unique in-house technologies that we're quite proud of. We make our own encoder read heads. We build our own linear motor assemblies. We harden our own rails. It's a pretty cool thing that we're able to do on site here in Vancouver. So now I'm gonna, I guess, kind of keep talking about just the individual modules, the basic modules. I'm gonna go through these fairly quickly. Again, just to give you an idea of what the standard parts are. So when we get to the next stage and start talking about some of the really cool things we can do to enable interesting systems, these are kind of the foundation of that. So this is another one of our linear motor, those direct drive stages. We use this for the focus. And again, this just gives us really high speed, high accuracy, really good repeatability, and like fine. So we can do a 20 nanometer step size on this. The repeatability for stages, for these stages as well, is also much more important than the accuracy. I think, yeah, the difference between accuracy and repeatability, most people really want repeatability. You want to be able to go back to the same position every time over and over again. That's really important. being able to go to an arbitrary position as you're putting samples in and out and swapping samples, those positions tend to move around a bit. So it's repeatability is kind of the key thing you want there. Our stages, for the microscopes, we include a magnetic counterbalance in them, and that just helps offset the force of gravity on the mass of the objective. So our stages use less power, less heat, less thermal expansion. Yeah, a neat piece of technology. We do have a IR laser focus tracking module. So if you're doing anything that's long duration, this will, long duration time lapse. This will basically prevent you from having any focus drift, particularly as, if you had it in a room like this, as the air conditioner comes on and off, if you're working at high magnification, high numerical aperture, you'll actually get some, without an autofocus system, you'll wind up with focus drift. So this graph is what happens when we've got, the red is the autofocus error, which we're basically measuring. We're taking the image, we're doing the Laplacian transform on the image and looking at its sharpness. And then the blue is the actual position of the stage. And you can see at the start, the air conditioner comes on and starts cycling. And so the stage is actually moving to actively compensate for the thermal expansion on the frame because of the air conditioning coming on and off. I guess one of the neat things about our Focus Stage 2 is it is objective agnostic. There are a bunch of manufacturers out there that will require expensive autofocus specific objectives. We don't. Ours just work. So that's nice. The filter cube turret, probably not as interesting for this group. So this is primarily to do the filter set switching for epifluorescence. If you are doing fluorescence, great. If you're not, then you just put a single bright field cube in it, or you use transmitted and you don't need to put any filter cubes in it at all. We also support dark field filter cubes. So if you are doing dark field epi illumination through the objective, yeah, we can do that. The system I'm leaving here has just got a basic bright field cube in it, but if you need something else, we can probably help you out. The junction block is quite a useful little tool. This basically adds an additional input or output from the optical path. So this is something that we've frequently used to put extra lasers into the optical path, or put a BB splitter in there and couple it to a spectrometer. That's a pretty kind of common use case with materials customers and applications. We have an objective changer, put multiple objectives on there. It's pretty straightforward. And then our illuminator modules. So we have the standard epi illuminator, which is on the system I'm leaving behind. We have a couple of different wavelength options. We can mix and match wavelengths if there is something that you need that is not one of our standard ones. Just let us know. There's a good chance we've done it before. It's a pretty straightforward thing to either add a new LED at a different wavelength, or if it's one that we've already got, do kind of a mix and match thing. We can couple our system to third-party illuminators as well, using a liquid light guide. It's a really common set of 3mm liquid light guide, super common standard. One thing to note about light guides is you do lose about half your illumination power going through them. So if you find an illuminator that's twice as powerful as ours, and then you plug it in, you won't actually get any real benefit. So yeah, like I say, yeah, if you are looking for a more powerful illumination, like go an order of magnitude, just 1 or 2x, 2 or 3x, not going to have a huge impact if you're going through a light guide. And we have transmitted illumination. Again, very straightforward. We're just shining a light through the sample. For materials, often not as relevant because oftentimes your samples are going to be opaque. Although we can do, like if you wanted to see through, again, like a semicon wafer, we could put like long wavelength NIR or a shortwave infrared LEDs in there, and that will go through a silicon wafer. Lighting controller does what it says on the tin. These also have a bank of TTL IO on the other side, so that makes it handy for controlling syncing third-party hardware and equipment. Zaber has a really slick Python API, and so we often have customers using our API and the TTL on our equipment as a means of automating other devices and hardware in their setup that either doesn't have as nice an API or just doesn't have one at all. A lot of our devices have those TTL inputs and outputs on them, and yeah, they can certainly make life very easy. And then kind of the last of the standard modules is, as a motion control company, that's really where our bread and butter is. We have a ton of other stages. We have rotary stages, we have linear, we have tip tilt, we have vertical lift stages, we have external controllers. We have this like little process controller that can drive heaters and solenoids and fans, and kind of any other DC load you can think of. So a lot of kind of flexible tools if you're looking to automate and integrate processes outside of just the imaging workflow. So now we can do the fun stuff. And so this is kind of examples of interesting systems that we have built for customers based on their needs. So taking our standard microscope, and so in this case, we had a customer that was looking for more wavelengths and faster switching between those wavelengths than we could do with the standard 6-position filter cube changer in that filter cube turret. So we mounted a pair of high-speed filter wheels, got them from 350 millisecond switching time down to 57, and then they got 10 different filter sets in there. And so yeah, that was a fun project to just shove a couple of big filter cubes into one of the microscopes. I think this is one of the coolest systems that we've done. Is actually, so we've built the system with a slider that can slide a mirror in and out of the optical path. So in this case, we've just got a standard dichroic notch filter that's coupling the autofocus laser to the optical path and then doing the standard epifluorescence imaging through the objective. But then when we slide the mirror this way, we're actually putting a mirror in there, and so we can switch to Raman spectroscopy. With our extremely repeatable XY stages, those linear motor XY stages, it means you can now do a visible spectrum scan of your image and get the actual visible spectrum, and then go back and do your Raman spectroscopy and know that the Raman and visible data will be precisely co-registered. And that's something that's really nice about those really high repeatability Zaber stages, is even when you're working at high magnification, you can save a lot of time by just doing the full area in one imaging mode, switching to the next, and then doing the full area in the other, and knowing that they're going to line up nicely, rather than having to do each point and switch between modes for each point. saves a huge amount of time when if you're looking to gather a large data set. We've done quite a bit higher power lasers in this. So with actually BC Cancer, we designed for them. They haven't bought it yet, but we designed for them a system to do basically laser microdissection. So single cell genomics with laser microdissection using this system. We've also done projects for a customer looking at MEMS devices on a wafer and carving a reticle into the wafer around defective MEMS elements. So yeah, if you want to get a laser, again, an additional laser into the system, particularly high power lasers, this is a neat way we can support that. Another, I guess this is I guess probably quite a bit more relevant to the materials characterization. And again, we've done Raman projects with this. Is if the precise angle and orientation of your sample matters, or if you've got a weirdly shaped sample and you want to make sure that it's always orthogonal to the optical axis, we can add additional rotation and tip tilt to the XY stage, so you can get the full 6-axis. 6 degrees of freedom for your sample. We do multi-mode simultaneously. So this was a customer that wanted to do high throughput spectroscopy and visible spectrum imaging at the same time. So they had a low magnification visible objective for kind of getting the, I guess, the context around the point where they were doing their gathering the data for their spectrometer. We do multi-camera, so that's a pretty common application if you are a pretty common use case for wanting to combine multiple types of cameras. So if you have, again, visible spectrum and infrared, seeing the surface and then looking for subsurface defects in a wafer. Or again, something like, I know we've had people just a standard camera and an event-based camera, or you could put a SPAD sensor on there, just mixing and matching. We also support very precise alignment in X, Y, and theta, so you can ensure you've got pixel level co-registration. So those two image sensors will line up perfectly, so the data from them will line up perfectly. We use quite, I guess, sort of industry standard Thorlabs based interfaces in a lot of our designs. That makes your life and our life very easy for if you want to build something custom, if you want to take one of our systems and build your own camera mount. We actually had a group, another group out of UBC engineering that built their own camera tube using the Thorlabs cage mount system. And we have just the dovetail block that lets you make that to off-the-shelf parts. So it makes, you can get creative, and you don't need a machine shop behind you to play with our stuff as well. So yeah, that dual camera mount, we can kind of set that up in a few different ways. We can just put a beam splitter in there and send everything to both cameras. You can put a dichroic and send short and long wavelengths to different cameras. We can also do switching, so you can just put a mirror in one, and if you want to switch between the two by just putting the mirror in or taking the mirror out, we can do that. We can get creative with wavelengths, so we can do NIR or UV. NIR is basically the same price as visible spectrum. UV is about 10 times visible spectrum, and that's just sort of the way it is. Like UV tube lenses, mirrors, and cameras, they're all about 10 times the visible spectrum stuff. So once you start getting to more exotic materials and coatings, and we can do it, but it is more expensive. But NIR is very straightforward. Another, I guess, relatively common request we get for materials, I think microplastics has been a pretty common one lately, is for adjustable polarizers. So we can put, there's 3 different places in the system where we can put a motorized adjustable polarizer. So we can do it under the objective, we can do it at the excitation port, and we can do it at the camera port. There's also some really cool cameras that we've worked with. The Sony MZR and MYR sensors actually have on-sensor polarization. So instead of being sensitive to red, green, and blue light, they are sensitive to 0, 45, and 135 degree polarized light, which is yeah, kind of a different way of looking at a different way of looking at the world. But then you can get at every individual point in a single shot, you can get all of the polarization data from across that entire your entire frame. You can get the angle and degree of linear polarization rather than taking a motorized polarizer and turning it multiple times and gathering that data. You can do this in a single shot, although you trade speed for spatial resolution because you are interpolating between those pixels rather than measuring it directly. But they're really cool cameras. Yeah, so those are some kind of examples of some of the interesting configurations we've done. If you saw anything there that is interesting, great. But I hope really what that inspires you is if you have an idea for some sensing modality that you need as part of your workflow, come talk to us and we'll help you do it. We have an in-house customization team, and yeah, so we love a good weird microscope. So come bring your crazy ideas to us, because they're actually not that crazy. The next little piece I wanted to talk about was as more kind of general, I'll say kind of best practices around high throughput, high speed imaging, and just kind of getting the most from one of these automated systems. We'll start with looking at like the tiled images. So if you're gathering a tiled data set, you're stopping, starting, and just stepping through your sample. Depending on your system and the step size, communication latency can actually become a big issue. This is like the easiest thing to take care of. If you're using Windows, there's just a calm latency setting in the COM port of most of the stuff runs on serial, so you can just turn that setting down and your thing will go a lot faster. It's surprising how much that can help. One of the other things that we do a lot of is, if possible as well, using IOs and triggers to drive things. Particularly like if you're syncing a camera and a motion control stage, rather than sending a signal from the camera to the PC, doing something on the PC, then sending the signal back to the camera, you can go straight from the microcontroller on the stage, the FPGA on the camera. It's way lower latency and way faster. So using those TTL triggers. So a good example of this is if I wanted to do a high-speed Z stack through the focus of a sample, tying the one I/O line on the focus stage to the camera, so that as soon as my focus stage has moved to its position and reports that it's settled, it triggers the camera to do the exposure, and then I tie one of the I/O lines on the camera back to the stage. So as soon as the camera says it's done exposing, it triggers the focus stage to move to the next position. And so you can get a really fast, low latency stack there. So that's definitely yeah. If you're really looking to push throughput, triggering is the way to go. I guess the main contributors to the total scanning time, I guess when I'm talking about plates, most of my examples are in the context of like a life science 96 well plate, but the same holds true for a wafer or any kind of sample that you're covering a tiled XY area. You got the trajectory, the settling time, the actual exposure, the communications port latency, and the actual time it takes to send the commands to the motion control device. Kind of understanding the relative magnitude of these is, if you're really pushing throughput, this is going to help you figure out where do you want to actually spend your time, what's worth fighting over a couple of milliseconds for, and what doesn't matter. So there's a couple of different examples. So we're looking at the same number of images at two different exposures at 96 and 384 wells. And so if we are doing short exposures, yeah, on the larger plate, like we can see, yeah, the trajectory is where we really want to spend our time. We want to figure out, okay, how can we minimize the number of moves? How can we minimize, really drive it faster, do input shaping? That's where we're going to spend our time. But if we've got less light, or right now we're starting, if we have a much longer exposure, well, there's kind of no point in oh no, oh no. There we go. Oh, we did this. We did this before. All right, we're back in business. Yeah, so if we're like the exposure time, if that's the killer, well, then we need to be looking at higher numerical aperture objectives, getting more light on the sample. You're going to get a way bigger increase in speed by pulling that down than you are by fiddling with COM port latency or settling time. Zaber gives you, we do give you a bunch of very useful tools for doing some of that kind of higher level optimization of motion profiles. So if you're trying to cover a big big area as quickly as possible. We can help you plot the kind of, I guess, target versus or your ideal versus what the stage is actually doing. This can be really useful if you are working with higher magnification optics or high numerical aperture, where you have a really small depth of field, and hitting that precise focus is really important. We have in our focus stage, we've got a 1 nanometer interpolated optical resolution encoder. And so you can get real-time position data from the stage, which is really useful in kind of applying the I guess the input shaping to minimize the settling time. So ideally, you want your stage to basically reach the target position and just stop there. It can be really tempting to just try and like crank everything up to 100 and just go as fast as you can. And then what happens is you overshoot, and then you undercorrect, and you wind up with the stage ringing, and then it takes longer to settle than you really want it to. And so backing things off a bit so that they just arrive exactly where they're supposed to and then stop, that's the way to do it. And these tools will kind of help you figure out based on how your system is built and the stiffness and the load you have on it, exactly how hard you can drive it before you start overshooting and sort of impacting your settling time. So I highly recommend if you are using those tools, this is the Zaber oscilloscope tool. Yeah, so this is a project that we actually did for a customer, and working through the initial the initial conditions. Then we got rid of the COM latency. That's like a 2-second setting to change in Windows. Got a little better. Yeah, got rid of again some device communication stuff. And then optimizing that actual motion trajectory and motion profiles, that gave a huge boost to the speed. So there really are very significant gains to be had. I mean, we cut the total imaging time with the same number of images and the same exposure time. We almost cut that in half. So it really is worth spending a bit of time. Like if you do have a large data set you're trying to collect, why spend longer doing it than you need to? I will also point out, actually, with this graph, there's some free microscope software out there called Micromanager. I don't know if any of you have run into it. Micromanager is atrocious in terms of like optimizing motion profiles and running quickly and throughput. It is just the software stack is really janky, and it's really slow, and it does a bunch of unnecessary movements. And so if you want to go fast, don't use Micromanager. But it's free, so people use it. But there are way better tools out there, and Zaber makes a free alternative as well, which is way better and way faster. So and just built into our software. So yeah, Micromanager. It's definitely out there in the community. There's some things it does really well, but if you're pushing throughput, it's not the right tool. The point I want to make here is really just about the order of operations and how they matter and can have a really big impact on your total scanning time. So what I'm showing here is with our standard filter cube changer, it takes 350 milliseconds to change a filter. And so if I want to image the same point at 3 different heights at 3 different channels, so I'm taking 9 images. If I don't have a very repeatable, or let's say, if I have a very repeatable stage, I know I can do 1 full stack on one color, move to the next one, do the next full stack on one color, then do the next full stack, and I know they will all line up. If you don't have that repeatability, I did it again. Oh dear. See if we can. All right, I'll try to do that again. If I don't have that repeatability and I have to do each position at a different wavelength, now I'm doing 3 filter changes per position instead of 3 across the whole set. And you can see that even just for those like 9 images, hypothetically here, we're taking basically 3 times longer because of that. And so as you start moving to, like in the real world, if you're actually doing a large tiled acquisition across multiple focal planes with multiple wavelengths, I mean, you're talking thousands of images. And so this is like literally the difference between, running it while you go out to get lunch and like sitting there waiting for it all day. So yeah, it really does add up. One of the newer, cooler technologies, which is really starting to come into the world of microscopy now, is line scan. This is, I don't know, kind of blowing people's minds that have been in the industry for quite a while, is just the speed that you can operate these things at. The technology that's really enabled this is TDI, which is, I guess traditionally line scan cameras were one line of pixels, and you would sweep them across your sample, and every 1 pixel of distance, you would read that 1 row of pixels out, and then move to the next one, and you would just build up your image 1 row of pixels at a time. With TDI, there's multiple rows of pixels, and so you get multiple reads of the same position now as you move across. So that enables you to basically integrate the brightness of each line it reads over multiple reads, and so you can go a lot faster. And so that's really kind of opened the door to this really high speed microscope imaging. And so this is an example of a project we did for a customer where we're looking at you see they're making electrodes on implantable electrodes on a wafer, and doing really high speed. The catch is that you need a really beefy computer to be able to handle that much data. So one of these high-speed line scan cameras can put out about 48 gigabits a second of data. So having a PC that's able to do something with that much data all coming in at once, that's the catch. Being able to trigger and synchronize your motion with your line rate, that is critical, because you need to trigger, the camera needs to trigger the sensor every 1 pixel of distance, so that you get an image that's basically the right aspect ratio, so you're not missing anything or you're not getting multiple reads of the same position. And so that is another thing that Zaber can provide, is we have controllers that provide encoder outputs in the format that a lot of these cameras are expecting. We have triggers that can interface with them. We also have kind of the cheat mode, which is our position velocity time tool, where you can just tell the stage, between these 2 positions, I want to be moving at this very specific velocity. And then you just tell the camera, my sample and my stage is moving at this velocity, and then it just works. And then you don't have to mess around with encoders or triggering and input scaling and all that. It just works. So that's definitely a tool that, again, it's just baked into our software, the position velocity time. Yeah, so we even give you a nice GUI and plot for what that looks like, and we have a couple of different ways to visualize the data. You can do multi-axis, so it makes building complex trajectories really straightforward. Where it makes sense to use line scan, it is super fast, but there's kind of a trade-off as your exposure time gets longer and as your magnification gets higher. It basically becomes a bit less of an advantage. And so, yeah, that really short sweet spot kind of, or short exposure, 10 to 20x magnification, that's really where you get the biggest uplift in performance from line scan. So that's also something to think about, because yeah, it's super fast and it's really cool, but it's not always the right answer. I think we're getting towards the end here, but I guess one of the last things in the kind of high throughput side I wanted to mention is the sample handling. Like, this is, I guess, sort of the next stage in that, like being able to cover one sample at a time. That's great. If you want to automate the process so you can run it overnight, that's, again, something we can certainly help with. 6-axis robots, I'm sure you've got a few of them around here. So there's another Canadian company, Mechademic, that make a really nice 6-axis robot. They're really flexible, programmable. They can reach all kinds of interesting directions, very accurate. They are also quite expensive. Gantry systems are much more affordable, but you really kind of have to know what you're doing, and they're sort of built for a purpose, and that is what they do. So they're not as flexible, but they're fast and they're affordable. Fortunately, with Zaber stuff, you can't always take them apart and put them together in a different way. And the last thing I wanted to just have a couple of slides here that I wanted to go over, because I am leaving the instrument here. So I just wanted to give kind of enough of an overview that you feel like you can jump on and have a go, basically. So we'll get this set up here, but really it's the microscope app in our Zaber launcher software. So just click on the microscope, and then you get the panel here, and you have all the controls that you'd expect. You can move your sample around, move your focus. You can save and load positions, control the illumination, all the basic functions. It should be pretty self-explanatory. Presets make life really easy. So there's this manage presets button up there. Presets basically let you build kind of application or sample specific presets where you can set illumination, objectives, focus parameters, step sizes. You can basically build kind of a collection of settings that you can apply with one click. So that's really handy. We use those as part of the automated multi-dimensional acquisition as well. So we've got, I guess, a few options for, you can either do a grid with just arbitrary point spacing. We can do tiling, where you've got a little bit of overlap between them, so that's intended to be stitched together into one larger image. You can just load a position file in with just CSV position values, or if you've saved a bunch of positions of interest, you can do it off the save positions. I've been playing with the position file, the CSV values. You can do some really cool stuff using the generative AI platform of your choice. Like, I've fed images or CAD models of samples in and told it, basically like, here's what I'm trying to do. Here's the dimensions of this in millimeters. Give me a position file that, or CSV file that has the positions to do this, and it's worked. So that's if you're doing some kind of interesting non-standard sample, custom consumables. That's something that a good, actual good use for those tools. We don't have camera control integrated, so we're camera agnostic. I'm just leaving a little basic camera here. The trick with that is, so the software will all be set up on the PC, but to switch it into for automated acquisition, you do have to set up the triggering. So there's a GPIO tab on the kind of camera settings thing, and we'll make this available. But those are the settings you want to apply, just to tell the camera that, yep, when I am triggered, I capture an image. It's pretty straightforward. And then you just have to set up in the camera recording window. Just tell it where you want to put the images that you save, and then every time our software triggers the camera, it'll save the image. And so it's pretty straightforward. The automated acquisition will run. Then one of the things we just added as well is the ability to export the metadata, which is very handy to help you do automated image stitching. So again, if you're trying to stitch a big image, the camera that we have left behind, those are the parameters that you want to feed into this box here. That writes those to the metadata, so that third-party software can basically use it to automatically stitch your images. So like ImageJ, we use that for our image stitching. It's free. It's widely used in many publications. And that'll take the position file from our metadata and automatically stitch the images. So yeah, there's a lot of the final precautions there. Basically, if you have any questions, if you're playing with the instrument, if you have any questions, just give us a call, send us an email. We have a dedicated applications engineering team. We want to help. So yeah, just feel free to have a go, and then if you can't find it in the documentation, let us know. We're happy to help. And I will turn it over to